I'll make this lecture in English, but it seems optimal for this audience. So this is the second part. Last time I gave you several examples of isolated systems. Today we'll talk about systems in a contact with a thermostat. I hope, yeah. Okay, so I should check if thermostat c'est écrit avec un H ou non? Oui, donc thermostat probably. I didn't prepare it in English, so sometimes So, last time I attracted your attention specifically on the difference between external parameters and interior variables. So here the external parameters will be temperature, volume, number of particles, and maybe something else. And interior variables, internal variables, which the system will choose for itself, are pressure, energy, well, chemical potential, and maybe something else. So the main difference is, as you see, that E and T changed places. Last time the system was isolated, so E was an external parameter fixed during the experience, and this time it's the temperature of the system that will be fixed from the exterior. But before we start talking about physical systems, I will make some additional remarks on entropy and information. So let us suppose that we have some experience with an unknown result, and we attribute different probabilities to different results. So let's say that there are n possible results with probabilities p1, pn. Since we're talking about probabilities, it means that we lack some information about the issue of the experiment. And the entropy is actually a measure of the lack of information. Last time I considered only one case when all states had the same probability 1 over n. That was the main postulate of the statistical mechanics for isolated systems. And in that case I simply defined US as k times log n. K times the logarithm of the number of the states. But today the probabilities will not be equal, so I have to say some more words. Well, there is a general formula. K is the K is it could be any constant, and in physics it's the Boltzmann constant. Yes. So there is a general formula. S is equal to minus K sum pi log pi. So I will try to justify why this is the only possible formula. Actually, there is a rigorous theorem that I will formulate but not prove. But the idea is that, well, if you have a very small p, pi, then if the issue of the experiment happens to be in this very improbable event, then it gives you a big amount of information, which is logarithm of pi. But this happens only with probability pi, so we have to ponder it in this way. And there are, well, this function satisfies several properties. Let me list some natural properties. First of all, S of 1 is equal to 0. If there is only one possible issue of the experiment, then we lack no information. So the measure of the lack of information equals 0. Right? Because if you take, well, logarithm of 1 is 1, so logarithm of 1 is 0, so S vanishes. Okay, if we have, S does not depend on the order of P1, Pn, which is also a natural property to expect from a measure of lack of information. Okay, then S of P1, Pn 0 is equal to S of P1, Pn. If we add to our experience an impossible issue that never happens, then actually the lack of information is exactly the same. There is nothing new. And if you see, if we substitute here p equals 0, well, logarithm of 0 is not well defined, but p times log p tends to 0 as p tends to 0. So it's the natural extension of this formula. Okay, then one more natural property. If we take n states of probability 1/n, this increases with n. Okay, if we have n states with the same probability, then of course the lack of information is increases as the number of states increases. And finally, there is one last property that I will write here because it's more complicated, additivity. Which says the following: if we replace every pi I by some pi I1, pi I, let's say Ni, in such a way that the sum of the Pij is equal to Pi. Okay, so if we take the same experience as before, but we add more indetermination, we divide, well, let's say here we have n boxes, and we land into these boxes with probability P1, Pn, but now inside each box we add some more boxes with some more probabilities. Okay, so then we have the following: S of this system Pij is equal to S of P1, Pn plus, let me see.
I think you must have Pij equals Pi times Pj.
Sorry? No. No.
Divide pi ij by pi a.
This is P1, Pn, and here we have another subdivision into P, well, this is Pi, and here we subdivide Pi into Pi1, Pi2, Pi3, and so on. So it can be a different subdivision for each box. It can be something like that. But I don't want to get the formula wrong, so maybe I'll look into into the book. Yeah, okay, so let's say that the sum is equal to 1, and then the probabilities are actually P1 times P11, P1 times P1 N1, P2 times P21, P2 times P2 N2, and so on. Okay, so it's a different normalization. I choose the sum of probabilities of boxes inside the sub-boxes inside each box to be equal to 1. And then I should have, so this is okay, and then plus sum from 1 to n, pi times s of pi1, pi ni. Okay, so I'll repeat it without formulas. The lack of information in this experiment, where I have some smaller boxes inside each box, is equal to the lack of information concerning the first experiment, where we have only the big boxes, plus the sum of lacks of information inside each box, but this lack of information is pondered by the by the weight pi.
So you expect lack of information after you complete the first step?
Yes. So we first perform the first step of the experiment and choose one of the boxes which fills in the lack of information here, and then with probability pi we land in one of the boxes and we have to perform another experiment with this lack of information here. Okay, so now theorem, maybe I write it here. Yeah, there is probably just one last property that I forgot, is that S is positive, non-negative. So this theorem is that the only expression, the only possible expression for S is k minus k sum of pi log pi with k a positive constant. So that's the only expression for the lack of information that satisfies these 6 properties. These 5 completely trivial properties, and the additivity property that is not so trivial but rather natural too.
Shouldn't you demand, as Yaglombs do, that this S with 1s over n is the maximum possible? The entropy maximal with
I think
probability.
I think it's enough. I think this is enough. But
it implies.
I think it does. I don't give you the proof, so I'm not 100% sure. Okay, so you could add another natural property that if you have n probabilities, well, n issues of the experiment, then the lack of information is greatest if the probabilities are 1 over n, which is also very natural. But I think it's not necessary. Well, it is another property of this formula.
So don't you think you need some kind of measurability or something in PI?
We have finite set. So
no, but it's a function of S. Yeah.
Maybe you could use some Hammer basis or something to change it somewhere.
Yes, I don't know. Yeah, I'm sorry. I didn't prepare the proof, so I'm not sure about that. But probably. Yeah.
Maybe you need some continuity or something.
Yes. Okay, so that was an introduction. And now we go back to our physical system. Okay, so first I should tell you what is a thermostat. And actually it is just any sufficiently big system. So our goal is to impose the temperature from the exterior, and to do that we just take a very big system whose temperature does not change in any noticeable way if we add or subtract some energy from it. So, well, last time I defined, well, if the thermostat is isolated, let's say thermostat, let's denote it by, well, if it is isolated, then last time I defined the temperature as the derivative of S with respect to energy, and here we want it just to be a constant. So the only thing we will use for this thermostat is that its number of, well, is that S is equal to some S0 minus E over T, where E is the energy of the system. So we have our system S, well, system, that's not denoted by S. Here we have the thermostat, and all this is isolated from the exterior. So the total energy is fixed. The system has some small part of it, E, and the remaining part of energy is in the thermostat. There is a minus because E is the energy that's in the system, so that is not in the thermostat. The energy of the thermostat is the total energy minus E. So S0 is the entropy that corresponds to the total energy, and then we subtract E over T. And the separation between the two allows heat to go through and nothing else. So this is fixed, but it allows heat to go through. And in that way the system is always maintained at temperature T. Okay, so now we must, okay, okay, now let us suppose that our system happens to be in some state, I don't know, is in some state with energy E. Then we count how many states, how many possible states the thermostat can be in. So the number of states is the e to the power s. So it has, okay, e to the power s0 minus e to the divided by t, and all this divided by k possible states. And according to the main postulate of the last lecture, all states have the same probability to occur. But all states of this complete system of the system here together with the thermostat. So it means that the probability of the states is proportional to the number of states of the possible states of the thermostat. So it is proportional to e to the power minus e over kt. Right? Because e to the power 0 is the common factor that I can discard. So this is the formula that replaces the main postulate for a system in contact with a thermostat. Now all states do not have the same probability as last time, but they have a probability that is proportional to e to the power minus energy divided by kt. Okay, so now we define the partition function z. Well, maybe. In Russian it is статсумма, статистическая сумма. It's not the same terminology. So this is the sum over all possible states e to the power e over kt. And again, in quantum mechanics this is really a finite sum that has a rigorous meaning. But since I don't want to talk about quantum mechanics, I will replace the sum by an integral over the phase space, the space of all possible states of the system. And F, this is called the free energy, equal to minus kt logarithm z. So this z now replaces big omega, and F replaces the entropy. They will play the analogous role in this, well, in this context of a system in contact with a thermostat. Yeah, maybe I should write it here. So now I must draw a parallel between this sum over states of e to the power minus e over kt, which is the main object of study in statistical mechanics if we fix the temperature from the exterior, and the sum over all states of e to the power is over h, which is the main object of study in quantum mechanics. So in quantum mechanics, the amplitude of probability of every event is given by the sum of all possible states over sum. Well, S is not the energy, S is what is called the action. But formally, these two expressions are very similar, and this is actually one of the reasons why statistical physics became so important. It is often not because we just want to study the statistics of some system. It is because it is another way to compute the same kind of integrals. Well, it's more or less the same integral, only it's easier. Compare, for example, the integral of e to the power minus x squared and the integral of e to the power I times x squared. So this one is the integral of a function like that, which is well defined and can be computed. And this one is an integral of a function like that. So it is called an oscillating integral. And it can also be defined because the areas of these of every wave becomes smaller and smaller, so actually it can be defined, but if you think how to compute this integral, you will invariably start by computing this integral, then putting some lambda here, and then trying to find the limit as lambda tends to the imaginary axis. If I put lambda here, it is easy to compute for lambda with positive real part. Then you can study the limit as lambda tends to the imaginary axis, and then it becomes meaningless when lambda has a negative real part.
Can't you just use the analytic continuation in lambda?
Yeah, yes. But anyway, when you have a problem in quantum mechanics, usually the way to look at it is to start by the analogous problem in statistical physics, try to solve it, and then try to find an analytic continuation, as you say. Well, to extend the solution. So in particular, although from the point of view of statistical physics there is no reason to prefer this situation of a system in contact with the thermostats to the situation of an isolated system, actually it so happens that this is the situation that everybody considers first. Well, it's really usually this Boltzmann distribution of probabilities is the first thing you learn in a course of statistical physics. Okay, so now now we have defined f. We have external parameters t, v, n, and so on. We have a function, the free energy of these parameters, and we want to define everything else. We want to define pressure, energy, entropy, chemical potential, and I will just introduce the notation beta is equal to 1 over kt. Sometimes it's easier to make computations in this way. And there is a formula beta over d beta equals minus t over dt. Right? That's easy to check.
How is this called in any language? What is the name of it?
I don't know if it has a name. Maybe. Yeah, I don't know. Inverse of the temperature.
Can you explain once more
Yes.
why we have to choose this function to describe the set of possible
You can ask in Russian if you wish.
такая функция, описывающая все равно состояние.
Почему именно f? Или почему?
Да, почему мы берем в таком виде?
Значит, okay, so the answer is that our system actually, well, okay. So it's the same reason as with entropy. So now every state is, well, last time I told you that every state has the same probability, so the system will naturally go to the situation where it has most possibilities to occupy most available states. And to follow this, we introduced S, which was the logarithm of the number of states. Here it is more or less the same thing, except that every state has a probability. So the system does not occupy each state with the same probability, it occupies different states with different probabilities. There is actually a competition between two effects. Usually, the larger the energy, the more there are states, but their probability becomes smaller and smaller. So there will be some mean energy where these two competing effects will come to an equilibrium. And okay, so we will look actually to minimize f. If we have, well, okay. At present, I didn't give you any properties of f. But maybe you should wait for some minutes, and you'll see that pressure and energy are just simply defined in terms of f. So maybe I can answer you again in 5 minutes. Okay. So first of all, I define the energy as d over d beta of beta f, which is equal to f plus beta d over d beta f, which is equal to f minus t df over dt. So this you can consider it as a definition, since the energy is not any longer an external parameter. Now it's an interior variable. I can just define it in this way. But of course, we would like to understand why this coincides with the true energy of the system. Well, in our situation, actually, the system has a fluctuating energy. It chooses its energy itself, so the energy can fluctuate. It can go from the system to the thermostat and back. But I say that this is the correct expression for the mean energy. So let me prove this. Mean energy. This is 1 over z, sum over the states, energy times the probability of the state. Right? This is the definition of the mean. So this is 1 over z, sum over states, e to the power minus beta e. And this should be exactly what I wrote there. Right? If we take, so this is d over d beta of beta logarithm z. Right? Is that true? Of So let me see. If we take logarithm z, it is, yeah, okay. Beta logarithm z, this is d over d beta of beta of what's the there is a missing beta. Do you see the, yeah?
Why is it beta logarithm z and not logarithm z?
Yeah.
Because it's beta f, which is logarithm.
Yeah, in principle it should be.
What is 1 plus beta and z d beta?
Yeah.
Почему там единица-то, а не
Да.
логарифм z?
Логарифм z, правильно. Well, I'm sorry, I have to look at in the book again. This is an unexpected place to. I'm very sorry. That's what happens when. But I think this should be done correctly. Okay. Yeah, okay, so that's where is that? So there should be no yeah, okay, I see why. I know why. You should have told me too, because here's the definition of f, it's just too far away. So beta f is equal to f over kt. So it's minus logarithm z.
That's what I told you.
Yeah. So here you have just logarithm z and everything is, and then everything is okay. Yeah. So that's because the f is not just a logarithm of z, but minus kt times logarithm of z. Okay, so now I think everything is correct. Okay, so now I can compute the entropy. Again, I can define the entropy as minus df over dt. But it would be more satisfactory to understand why it coincides with the entropy that I introduced at the beginning of the lecture. So let me prove that. The entropy should be equal to minus k sum pi logarithm of pi, where pi's are the probabilities of the states. So in this case, the probability of each state is e to the power minus e over kt over z. And then you should multiply by the logarithm of the same thing, which is minus e over kt minus logarithm z, right? So now I can cancel the minus signs and write it again. E to the power minus e over kt over z times e over kt plus, maybe I can immediately replace logarithm z by minus kt minus f. Okay? I use the equality that logarithm z is equal to minus f divided by kt. So this is what I get. Okay, so now E minus F is actually written here. If I take, okay, so now I take the average. I first separate it in two terms actually. So this term here gives me K 1 over Z sum of K 1 over T actually 1 over T 1 over Z e to the power e to the up minus e over kt. Right, so this is the first term. And the second term gives, again, 1 over t, f, that I can put here, sum e to the power minus e over kt over z. But this is equal to 1. This is equal to 1, and this is the sum that I have just computed. This is equal to, this is the average energy, so this was equal to F minus T dF over dt. So finally I get F over T minus dF over dt and minus F over T. And this is equal to minus dF over dt, which is what I wanted. Sorry, it's the first time I make these computations on the blackboard, so they don't go out very smoothly. But I think it's rather clear. I write the expression of the entropy, then I compute, and I obtain this. Okay. And finally, I define the pressure and the chemical potential. So the definition of the pressure is minus dF over dV, and the definition of the chemical potential is dF over dN. So now I can turn back to your question. Why does this definition correspond to the true pressure? Last time I gave you the definition of the pressure for an isolated system. So as you see here, the definition is even simpler. And again, I would like to understand why this corresponds to the correct pressure. So to do that, I put, again, two systems in contact. But I allow them to exchange volume. So here is the separation that can move between the two. Then here's the thermostat. And I would like to see in which direction it is going to move. Which volume will increase and which volume will decrease. And the reason is, well, the explanation is exactly the same as the last time, except that it is even simpler, because last time I had to take into account the energy that was exchanged between the systems when one of them pushed and the other pooled. And here I do not have to take the energy exchange into account, because anyway both systems can exchange heat with the thermostat here. So any energy that can go from one system to the other because of the work it performs will be absorbed by the thermostat and given back, or maybe, well, the thermostat will decide by itself how to distribute energy to the systems. So here the only thing that happens is that they exchange volume. And now we simply compute the not the possible number of states, but the possible weighted number of states. The weighted number of states with weight e to the power minus e over kt is equal to z1 times z2. So Z1 is the weighted number of states of the first system, Z2 is the weighted number of states of the second system. And since it so happens that when we add two energies, the weights are multiplied in e to the power minus e1 over kt multiplied by e to the power minus a2 over kt is equal to e to the power minus a1 plus a2 over kt, e1 plus e2 over kt. So the weights are compatible with each other. So we just must understand whether this number increases or decreases. So I say that it increases, well, the logarithm. First we take the logarithm, let's say minus kt times the logarithm, to obtain f1 plus f2. So now I say that if f1 plus f2 increases, that is good, decreases, that is good, and if it increases, that's bad. So when f1 plus f2 decreases, that means that, because of this minus sign, that the number of possible states, the weighted number of possible states, increases. So that's the direction in which the system will evolve naturally. Okay, so we just compare df1 over dv and df2 over dv to see which is greater. And the greater one will win against the weaker one. And again, the same holds true for this chemical potential, except that as last time there is no alternative definition, so this should give you an intuitive understanding of what it is. Again, if the systems can exchange particles, the one with a greater chemical potential will have the tendency to give its particles to the one with a smaller chemical potential. Right, so now, yeah, there is one more remark. The name free energy is actually meaningful because it means energy that is free to perform work. If we have just some gas gas with the temperature, same temperature as the outside, then it has a lot of energy, because its particles are moving, but this is the energy that we cannot use. And free energy measures the energy that can be used to perform work. Okay, so now the main example of today, I have Okay, I have 20 more minutes. I think it should be enough. Because well, it is not possible to give a lecture on statistical physics without mentioning phase transition. Here it will be the transition from liquid to vapor. Да, фазовый переход, да.
Vapor это пар.
Да. Из жидкости в газ, да.
Steam.
What?
Is it a steam?
I think it's vapor, no. Steam is what a steam engine is. I'm not sure if you write it with a U or not, but probably you write it one way in English and the other way in America, so okay, so, and there is the model everyone uses for that, which is a very simple model, actually not very realistic, but that shows all the characteristic features. So that's the one I'm going to use too. It's called the van der Waals gas. Probably have already heard about it. Okay, so we have n particles in a box. And I want to compute the partition function z. So first of all, I start with 1 over n factorial, not to forget about it because the particles are indistinguishable. And 2 pi h bar to the power 3n, which is the unit of volume in the phase space that I use. So again, in quantum mechanics it has a precise meaning, but for us it's just an arbitrary constant. And then I have to take two integrals, one over the positions of the particles and the other one on the how do you call that in English? Quantity of movement, probably. L'impulsion, quantité du mouvement, okay.
Momentum.
Momentum, right, yeah. So the second one over the momenta of the particles. This one is easy, it's the usual energy minus sum of pi squared over 2m divided by kt. And the second one is precisely, well, it's something that we must model. So at present I will just write minus the potential energy that depends on the positions of the particle over kt. So if we want to model the phase transition between liquid and vapor, we can no more consider that there is no interactions between particles. When there are no interactions between particles, that's the model for the ideal gas, there are no phase transitions. The phase transition is precisely due to the fact that there is an interaction between particles. So we should put something here. And actually, okay, so let's start with this integral, because this is the easier one to compute. It is equal to 2 pi m kt to the power 3n over 2. So nb, nota bene, the integral of e to the power minus x squared over 2 sigma squared dx is equal to square root of 2 pi times sigma. This is the formula for the normal distribution with variance sigma. And this integral is just a product. This can be factorized over every coordinate, so this integral is just a product of 3n integrals like that. you compute every of them, you obtain every time the same answer. And so here is the final answer. And here we use the oversimplified approximation. I think I can write it down.
What is the function?
U is the potential energy.
And it is not yet specified.
It is not yet specified, yes. And actually I'm not going to specify it, I'm going to specify the answer. V minus V0 e to the power minus U0 over KT to the power n. So what does that mean? It means that every particle can find itself not in the volume V, but in volume V minus V0, because the volume V0 is occupied by other particles. And on the other hand, there is some attractive energy between particles, which is usually particles that are far away from each other have a very weak attractive force. So this is some energy that depends on how many particles there are in the vicinity of a given particle. So maybe now I can even write U. So U is something like that. It's really a yeah. Maybe even, yeah. So that's the energy of interaction between two particles. We approximate it in this way. We suppose that there is a wall, that particles are solid balls that cannot go one into the other. So this is the volume occupied by these balls, and every particle should avoid to be in contact. Well, it cannot. Two particles cannot be in the same place, and then if they are far away from each other, then there is a weak attractive force. And since there are many of them, the attractive force only depends on the concentration of the particles in our box.
So your U under the exponent is a sum of pairwise interactions?
Yes. Yes. So this is an integral over all possible positions of all other particles. I fix one particle, and then depending on the density, I can integrate over all positions and get some negative potential energy. So actually V0 will be equal to some constant B, that is the constant, really the constant in the model, times n. B is the volume occupied by one particle, and U0 is a negative energy, as you can see it here, minus A times n over V. So n over V is the density, and this is the attractive potential, so it depends on the density of the particles. Okay. Have 15 minutes. Maybe I should erase that. So now I compute the free energy, which is minus kT logarithm z, and luckily I computed that at home, so I don't have to do it on the blackboard. It gives the following. Well, I have two forms of the answer. I guess I can write only the Okay, I'll write down both. MKT 2 pi h squared to the power 3/2 v over n minus b plus 1 plus an over ktv. And as the last time, I separate it into the interesting part and the uninteresting part. And kt logarithm t to the power 3/2 minus nkt logarithm v over n minus b minus an over an squared over v plus a constant. So everything else, there is this one, there is the no, one is included somewhere. There is well, this logarithm of I think I should, yeah, something like that actually. So there is this one, there is the logarithm of m times k over 2 pi h squared to the power 3/2. This is not interesting to us. Okay, so I don't know if you can see that the computation is right. I can try to, well, okay. I think I just let you check. Maybe from far away you can see it in. It's easier to see. Just one thing. There is this v minus v0 and 1 over n factorial. So 1 over n factorial, you use the Stirling formula. Logarithm n factorial is equal to n logarithm n minus n. And so together they give this and this one here. Okay, using that v0 is equal to bn. Right, so now I can compute p, which is equal to minus df over dv, which gives me n kt over v minus bn minus a n squared v squared. So there is the state equation of this gas, p plus a n squared over v squared times v minus bn equals nkt. And if you take the parameters a and b to be equal to 0, you find the equation pv equals nkt, which is the equation of the ideal gas. So if you assume that the particles occupy no volume and that the there is no interaction between the particles, you take both a and b equal to 0 and you find the state equation of the ideal gas. Okay, so now I think I'll erase this. Now finally I can show you the phase transition. Okay, so let us fix T, fix the temperature. and draw f as a function of the volume. So there are two terms. This term is constant if temperature is fixed. This term is also a constant if temperature is fixed. So there are these two terms that I will draw. The first of them, the logarithm, is something like that. Right? That's Bn. And the second one is something like 1 over V. So something like that. And then depending on the temperature, maybe I should attach letter T here. The higher the temperature, the greater the coefficient of this logarithm. So if the temperature is high enough, the logarithm, well, the graph of f will more or less follow this logarithm, because it will have a big coefficient, and this part of the curve, well, it's bounded, it won't influence very much. So if temperature is big enough, you will just have a graph like that. But if the temperature is small, then this part of the graph will win, except very close to this critical volume Bn, well, to the smallest volume Bn, because this function tends to infinity, so it will win anyway. But it will win only in the very end. While at the beginning, the graph will follow this curve. So we'll have something like that. We start with this, because this tends to 0. Then it goes down. And then suddenly in the end it goes up again.
And what is the critical point?
The critical temperature, you can compute it. You can, well, you just ask, you should write the equation that df over dv is equal to 0. Okay, the physical meaning, yeah, I'll explain that in one moment. So now I'll erase the picture and draw again the large graph of f with respect to v for small temperature. So here there are, okay, yeah, well, this is, when you look at this graph, you can immediately see that there is a problem, because there is a region when it is not convex. Between here and here, more or less, these are the inflection points. So here I have dp over dv, which is equal to minus d2f over dv2 positive. And last time I explained you that this was a problem. If the pressure grows with the volume, so I increase the volume and the pressure increases. And if I decrease the volume, then the pressure decreases. So this means that between these 2 points, the system is unstable. One half of the system increases slightly, the other half of the system decreases slightly, and then this process continues on and on. So one part of the system will decrease and find some better states to be in, while the other part of the system will increase in volume and find its own state. So how will it happen in practice? there are, okay, I should draw the common tangent, the double tangent to this graph. So if we fix the volume somewhere here, let's say, suppose that we fixed this as the volume for our system, then the system can find itself in this state, and this state is actually stable because I am still in the convex part of the curve. But it is not the state with the smallest possible f. So there is actually a more interesting state for the system to be in, the state where the state where there are more microscopical states, where the z is greater. And this is here. So if I call this alpha and this beta, it means that the system separates into alpha over alpha plus beta and beta over alpha plus beta. And this part of the system should be in this state here, while this part of the system should be in this state here. So this is gas and this is liquid. Sorry, it's exactly the opposite. The one with the smallest volume, of course, is the liquid. So in this case we see the following behavior. There is this stable region where the system in the gas state. Then if we decrease the volume more and more, the system will still be in a stable state, but not in the best possible state. These are called metastable states or oversaturated gas. And this is actually possible. If you take gas and you put it in the, well, if you decrease its volume very cautiously, then it will still be be a gas, but then you can put just one drop of water in it, and it will suddenly condensate into water. So this is what happens in this region. In this region here, until the inflection point. Then there is this region between the two inflection points, where the system cannot be homogeneous. It is completely unstable. If you try to put the system in the homogeneous state, one of the parts will immediately begin to inflate, and the other will begin to deflate. And so it will separate into two phases. Then there is this piece that corresponds to overheated liquid, which is also possible. So if you take water, and if you heat it very cautiously, you can arrive at temperatures higher than 100 degrees without it boiling. But if you put any impurity into water, something like a grain of sand, or just I don't know, even if you knock it with a hammer, it will immediately, part of it will immediately evaporate. And finally, starting from, no, it's okay. And so starting from this is the stable liquid behavior. But this happens only for small temperatures. If the temperature is bigger than some critical temperature, then there is no phase transition at all. So then we obtain the graph like that. That is convex. So the pressure always increases if we decrease the volume, as it should be. So for high temperature there is no difference between gas and liquid. And again, it is possible to make experiments to take, well, that's an experiment that our physics teacher showed us. Once you take some liquid, you show that it's really liquid by splashing it. You can hear it making in the bottle. Then you heat it, and then you condensate it again. Sorry, what should you do? So you obtain, yeah, okay, so you obtain a gas without noticing it. So so you heat it, it's still, well, you heat it, you don't see any phase transition, then you increase the volume, then you cool it again, and then you decrease the volume and you see it condensate. So it is possible to go from liquid to gas. Let's say, I don't know how to draw it, okay, but it's possible to go from liquid to gas without any phase transition. If you start by heating your system to a high enough temperature. And at a high temperature there is no difference between liquid and gas. Okay, so I think may take just one more minute with no more computations, because I promised in the course announcement to tell you what happens with the boiling point of water if you add salt into it. So we'll draw three. I will just draw three pictures and give a qualitative explanation. So here is water plus salt. And here is a separation such that water can go through. Oops. But not salt. Then what you find is that the level of water with salt raises higher than the level of pure water. I won't make any computations, but I will just explain why. Because water with salt has many more microscopic states than water without salt. Because you must choose where you put the molecules of salt, well, the atoms, the ions of salt. So it is more interesting for the water to be with the salt. There are more states if you put more water here. And then it is compensated by the fact that you need potential energy to raise the level here. Of course, if you put the levels on the same level, the system will have less potential energy, so there will be more energy for the heat. So these are two effects that should compensate. The first effect is that water wants to be with the salt. The second effect is that there are more states if you have more energy for the molecules to move. So there is some equilibrium between the two. And you see the pressure here higher on the right than on the left. That's the first experiment. And the second experiment is you try to freeze or you try to boil salted water. And again, well, if you freeze water, it forms a crystal of ice, and there is no salt in this crystal of ice. So when you freeze salted water, you should first separate water from ice, and then freeze pure water, which is more difficult than just freezing pure water, because water with salt has more states than pure water, while ice has just the same number of states in both cases. So salted water freezes at lower temperature than pure water. The water in the ocean freezes at -2 or -3 degrees. And it's the same thing with boiling the water. If you boil water with salt, the salt will stay inside the water. So the water will have more states, while the vapor, it's still the same vapor. The salt does not evaporate. So again, before boiling salted water, you should separate water from salt. And this is more difficult to do, so the boiling temperature of salted water is higher than the boiling temperature of pure water. Okay, thank you. I'm late again, but only 5 minutes late. Are there any questions? Yeah. No.
Is this situation physically realizable to make such an experiment that water can go through but not salt?
Yes, it's realized every time you sweat. after you play football. The mechanism that your skin has to sweat is to put some salt on the outside of your skin, and then the water from the cells goes outside and evaporates, and that is cooling you. So it's actually easy to realize in everyday life. You just have to run for some time.